So limits compared to calculus 3 and 1, they're slightly different because you can actually prove that the limit does not exist in calculus 3. Well, you can prove that it does not exist in calculus 1 as well. But for calculus 3, you have to prove it if it doesn't exist. And most of the problems that you're going to be solving probably doesn't exist. There's different methods to solve these limits, but sometimes you can just plug in the limit, just plug in the value, and you'll get some constant. And that's how you first learn how to solve for limits in calculus 1, and you can still do that in calculus 3, but I'm not going to cover those questions because that's literally just algebra. But sometimes you can also algebraically manipulate different equations to get the answer that you want. So let's just say that xy approaches 0, 0, and the function that we have is x squared minus y squared over x plus y. Well, this function is equal to x minus y times x plus y. So this is top numerator part of this fraction is a difference of squares. And I should be writing the limit symbol, and I will right now. So what happens? Well, we can actually factor out x plus y, and we can get just x minus y. And now we can just plug in the values. If you just plug in the values, you get 0, 0. 0 minus 0, which equals 0. So in some cases, you could just find the limit. In that case, the limit did exist. That limit did equal 0. But in different cases, you can actually approach a limit with different paths. What do I mean by that? Well, in this problem, I'll show you what that looks like. So for this problem, you can approach a limit with different paths. So what do I mean by that? Well, let's say one of the paths is m of x. So function mx gives you the value of y that you're approaching the limit upon. So let's draw the graph, what this looks like. So this is 0, 0. But what you can actually do is set m. Maybe you set m. M is some function. M is some variable that you can change. It's the slope of this function. But let's say m is equal to 1 here. So m is equal to 1. And the limit will be approaching along this line here. Let's draw another line. What if this line, what if m was -1, let's say? Well, it will be approaching along this direction here. But here's the thing. Whenever you're approaching with the limit, you're just getting closer and closer and closer and closer to the point you're trying to measure. And along these two lines, the limit is actually different. Not in this case, but it can be different. I'll show you more of those examples like that later inside this video. But let's show you how to solve this basically. So let's plug in x for x. X just stays the same. But y values are replaced with m of x. And if you do that, you get something that looks like this. Let's just keep using some algebra to simplify this. You factor out the x squared to get this. If you factor out x at the bottom, you get 1 plus x times 1 plus m. You can actually factor out this x squared, and you can get x times 1 plus m squared over 1 plus m. Well, what can you do with this? Well, you'll actually rewrite this function as a limit of x approaches 0. And the reason why is because there's no more y value. Y is in terms of x now. And if you do that, you get 0 times 1 plus m. Nope. You don't plug anything in yet. You get x times 1 plus m squared over 1 plus m. If you do this, you get 0 over 1 plus m, which always equals to 0. Unless m is equal to -1. When m is equal to -1, this function does not exist. Because it would be essentially equal to 0 over 0, which you can't be equal to 0 over 0. So this function does not exist when you're approaching along the path of m -1. But for every other path, you're Gucci. I can't believe I just said that. So it's green for all these other paths. Yes, you get some value. But when m is equal to -1, no! It does not exist. This entire thing messes up. So if you prove that, that means this limit up here does not exist. Because not all values are equal to the same thing. You got unlucky here. This function's unlucky, but only when m is equal to -1 is the values of this limit different. And that does not exist. Let's go on to the next problem. The limit as x, y approaches 0, 0. And for all these problems, yes, I'm going to use 0, 0. X squared plus y squared. So for this, you can actually, let's draw the graph again so you can visualize this easier. This is our point that we're trying to approach. What if we approach the limit from the, let's say, x-axis? Yes. What if we try to approach this limit from the x-axis? So from the x-axis, all x values are equal to 0. Correct? And y is just anything. So y will stay equal to y. And if we do this right here, if we approach from the x-axis of this function, what do we get? Well, if we plug in 0, just keep y, y. Plug in 0 for x, keep y, y. You get 0 over y squared here, which is just equal to 0. Correct? That's not all the work done. Because now you need to find another path that will make this function not work. Let's draw actually another graph for this, because this is the path we're going to take this time. What if the path we're going to take is, I don't know actually. Yeah. Let's take a path of this and this again. So for these two paths, let's say, actually, no. For this path, yes, this. For this path, y, right here, this function is just y equal x. And if y is equal to x, let's actually write x equal to 0, y equal to y. This looks like a 6. Oops. Let's fix that. Kind of wasting time here fixing tedious things like that, but I don't want anyone to be confused. So for this function, y is equal to 0, we're approaching along here, and x just staying x. So what happens if we do this? Well, if y is equal to x, correct? Let's rewrite everything here. Y is equal to x. We substitute all these values in. We get x times x. And x just stays the same because x is equal to x, but y changes to x. So what happens here? Well, this turns into x to the power of 2 over 2 times x to the power of 2. And if you can actually see this, you can factor out the x squares, you can get 1/2. And do you see these two answers here? These two answers are not equal to each other. They are not. Therefore, this limit does not exist. So, for this limit right here, we approached along the x-axis. Oh shit, it's not the x-axis, this is the y-axis. I'm so dumb. I can't believe I didn't say x-axis this entire time. But this is the y-axis. We approached along the y-axis, and guess what we got? 0. What happens if we approach along some function like this linear function, y is equal to x? We get 1/2. Therefore, our limits do not exist. Let's do another one. Let's do limit as x, y approaches 0, 0 for x squared minus y squared over x squared plus y squared. So for x squared plus y squared, let's think of something. Well, let's draw the graph again. Easier to visualize, and we're approaching this red dot here. Let's say we approach this maybe again along the Will that work? Let's do along y equals x. And honestly, this just comes down to practice, being able to decide the paths that you're going to take. It will be different for different questions, but being able to just see the algebra behind this beforehand is pretty useful skill to have. So this function is equal to y is equal to x, and let's just keep x equal to the same. So if we set x equal to x and y is equal to x, what do we get? Well, x stays the same, y turns into x, and what we get is this right here. 0 over 2x squared, which is equal to 0. So while approaching this function from y is equal to x, and we're just keeping x the same, you get 0. Now, can you get another answer from this? Yes, you can. You can actually get another answer from this. And let's show you that graph. So the previous question, we approached from the y-axis. I don't know. Let's just pick the x-axis this time. Why not? Both of those will work. Let's approach along the x-axis. And when you have the x-axis, y is equal to 0 all the time, and x just stays equal to x. So if we try this, y is equal to 0. We can try to plug in the values of x minus plug in the values of 0 for y, get x squared plus 0 squared again. So this is x squared over x squared, which is equal to 1. And do you see these values again? 0 does not equal to 1. And due to that, the limit does not exist. So if we approach from two different paths, the limit can change. And what we're trying to prove is that the limit changes from two different paths, and if we do that, the limit does not exist. Which most problems that have like fractions that look like this that you can't simplify will be does not exist as the answer. Let's move on. Limit of x approaching y. No, x and y approaching 0, 0 for, oh, this one's a little more tricky because we're actually going to use quadratic functions for this. So, contrary to your current understanding, you can actually approach functions using quadratics. Now, what does that look like? Well, let's try that out. Let's say, let's approach this function with y is equal to x squared. I'm trying to draw a parabola here. So we're approaching this point with the parabola, and y is equal to x squared here, and x is just equal to x. So x can just equal, can just vary along this value. And if you do that, x is equal to x, y is equal to x squared, what happens? Well, you have x squared, and you substitute y with x squared. X stays the same, but you substitute y with x squared, and you get this. X to the power 4 over x to the power 4 plus x to the power 4. If you keep going, you get 2x to the power 4, and you can actually factor out x to the power 4 to get 1/2. Now, how do I get x squared? Well, from this and from practice, you'll be able to see that there is going to be two factors that you can actually cancel out from the numerator and denominator of this fraction by using x squared for your y value. Let's draw another graph. What's some other path that we can take? Well, some other path we can take is a path that will set possibly the numerator to 0. Because we already have this value of 1/2, why not try to just set the numerator to 0 without setting the denominator to 0? And if you have some value of 0 with some real number or some constant at the bottom, not even a real number, even a function at the bottom, right? the value will always equal to 0. And if our value is equal to 0 for that path, then this limit does not exist because 1/2 does not equal to 0. And I'll show you what I mean by that. What if we approach along, I don't know, the x-axis? Well, for the x-axis, y is equal to 0, and x just stays equal to 0. So x just varies along this graph. So if you plug these values in, y is equal to 0, x equals 0, x equal to x, sorry. You get x squared times 0, x to the 4th plus 0 squared plus 0. And you get 0 over x to the power of 4, which is just equal to 0. And do you see these two values here now? 1/2 and 0 do not exist. Hey, I mean, they're not equal. Shit. So limit does not exist. There you go. So you're just trying to approach this limit with two different paths. These paths are just determined by these functions here. Drawing it out will help a lot easier, will help you a lot more. But let's move on. You probably don't have time to draw if you're at the exam doing this. So use your algebra skills to look ahead and see which paths are the easiest to take. Plus y to the power of 6. Okay, for this one, it's slightly different than the ones we've been doing. But for this, maybe you've noticed this already, but you can actually take the path of x being equal to y to the power of 3, which will look very weird. But this path, and I'm just drawing the visuals. You guys don't need to draw the visuals, but this path looks like this. And just y is equal to y for this. So what happens if we do this? Well, if y is equal to y, and x is equal to y to the power of 3, get some function that looks like this. So y to the power of 3 squared plus y to the power of 6, which is equal to y to the power of 6 over y to the power of 6 plus y to the power of 6, y to the power of 6 over 2 times y to the power of 6. What you notice is you can actually factor out y to the power of 6 to get 1/2. So if you're approaching along this path, the limit is equal to 1/2. What if you approach along, again, some value where the numerator is equal to 0 but the denominator isn't? Well, I don't know. It's up to you. Oh, you picked y-axis? Okay, let's approach along the y-axis. So when you're approaching along the y-axis, x is equal to 0, y is equal to y. So let's plug everything in for here. So x is equal to 0, so x 0, y to the power of 3, y stays y, 0 squared plus y to the power of 6. You get 0 over y to the power of 6, which is equal to 0. And as you can tell, 0 does not equal to 1/2. So the limit does not exist when we approach with two different paths. So let me recap. A goal of yours when you're trying to prove that these limits do not exist is to take different paths, and if these paths give you two different values, well, your goal is reached, your limit does not exist. But keep in mind, this is not always the case, because sometimes limits will actually have values, and sometimes you can choose two different paths and the limit will exist, or the limit will appear to exist. Like, let's say maybe our answer for this one was 1/2 down here, right? If it was 1/2, then you might think, shit, the limit exists, it is equals to 1/2. No, it doesn't. Maybe you should take another path that looks better and try to prove that it does not exist. So if you have any questions, put it down in the comment section. Hope you learned something.